Hello, my dear students. Welcome to IKSR chemistry classes. In this video, we will discuss molecular orbital theory applied to octahedral complexes. The molecular orbital theory is the most complete theory to explain the nature of metal ligand bond in coordination compounds because it incorporates the possibilities of both ionic and covalent character in the metal ligand bond. Let us see first of all the postulates of molecular orbital theory. In an atom, the electrons reside in atomic orbitals. Similarly, in a molecule, the electrons reside in the molecular orbitals. It means in atom, electrons are present in atomic orbitals, while in the molecule, the electrons are present in molecular orbitals. The atomic orbital belongs to a single atom, while the molecular orbital belongs to the molecule as a whole. The electron of an atomic orbital is influenced by only one nucleus. This is the electron present in 1s atomic orbital of hydrogen atom. This electron is influenced by only one nucleus. But the electron of the molecular orbital is influenced by more than one nucleus. This is 1s sigma 1s molecular orbital of H2 plus ion, which contains two nucleus and one electron. This electron is influenced, this electron of H2 plus ion present in sigma 1s molecular orbital is influenced by two nuclei. It means the atomic orbital is monocentric. It has only one center, while the molecular orbital is polycentric. It has more than one nucleus. In the present case, this sigma 1s molecular orbital has two centers. The molecular orbitals are produced by the linear combination of atomic orbitals of comparable energies lying on two or more atoms which may be same or different. It means the molecular orbitals are produced by the linear combination of atomic orbitals which must have comparable energies, and these atomic orbitals are present on two or more atoms which may be same or different. The atomic orbitals taking part in the linear combination should have the same symmetry property about the internuclear axis. The atomic orbitals which take part in linear combination producing molecular orbitals must have the same symmetry property about the internuclear axis. It means if the two atomic orbitals taking part in linear combination are rotated about the internuclear axis, the sign of lobes of both the atomic orbitals should change or not. Let us illustrate it taking a few examples by representing them diagrammatically. This is 1s This is s atomic orbital. This is also s atomic orbital. Both of these have positive wave function sign. If these two orbitals are rotated about the internuclear axis, the sign of the lobe of two orbitals will not change. Positive will remain positive and this positive will also remain positive after rotation about the internuclear axis, and hence these two atomic orbitals have the same symmetry property about the internuclear axis and their linear combination is possible. Similarly, s orbital and p orbital can take part in linear combination because both of them have the same symmetry property about the internuclear axis. On rotating about this axis, the sign of lobes of both the orbitals will not change. But this type of linear combination of s orbital or and p orbital is not possible because if these two orbitals are rotated about this internuclear axis, the sign of lobe of this orbital will not change, while on doing so the positive lobe will come downwards and thus the sign of lobes will change, and hence s and p orbital cannot take part in linear combination in this orientation. Similarly, two p orbitals, this p orbital has horizontal alignment while this has vertical alignment, and if these two p atomic orbitals are rotated about this internuclear axis, the sign of lobe of this orbital will not change while the sign of lobe of this orbital will change. Positive will come downwards and this negative will come to upward position, and hence this combination of two p orbitals is not possible. But if both the p orbitals are in vertical positions, that is parallel to each other, the combination is possible because on rotating about the internuclear axis, the signs of both the orbitals will change, and hence this linear combination is possible. Similarly, if both the p orbitals are in horizontal position, this linear combination will be possible because the signs of lobes of these p orbitals will not change during rotation about the internuclear axis. And hence these are some combinations of atomic orbitals whose linear combination are possible or not. The number of molecular orbitals produced is always equal to the number of atomic orbitals taking part in linear combination. For example, if two atomic orbitals take part in linear combination, two molecular orbitals will be produced. If three atomic orbitals take part in linear combination, three molecular orbitals will be produced. One of these two MOs has lower energy than both the atomic orbitals. It is called bonding molecular orbital. And the other MO has higher energy than both the atomic orbitals. It is called anti-bonding molecular orbital. Please note that the molecular orbital having lower energy than both the atomic orbitals is called bonding MO, while the molecular orbital having higher energy than both the atomic orbital is called anti-bonding MO. Diagrammatic representation. This is atomic orbital of atom A. Psi A is atomic orbital of atom A, while psi v represents the atomic orbital of atom B. These two atomic orbitals take part in linear combination producing two molecular orbitals. It is psi b. It is it has lower energy than both the atomic orbitals and hence it is bonding molecular orbital, while the other molecular orbital psi a has higher energy than both the atomic orbitals and hence it is anti-bonding molecular orbital. Psi b and psi a are molecular orbitals of molecule AB. The bonding MO is produced by the addition overlap of atomic orbitals, while the anti-bonding MO is produced by the subtraction overlap of atomic orbitals. It means bonding MO is produced by addition overlap of two atomic orbitals, while the anti-bonding MO is produced by the subtraction overlap of two atomic orbitals. In the formation of bonding MOs, two atomic orbitals have similar wave function sign, while in the formation of anti-bonding MO, two atomic orbitals have different wave function signs. If an electron enters bonding MO, the electron density between two nuclei increases. Let us square both the sides in equation 1 on the previous slide. Psi v square will be equal to psi a square plus psi b square plus 2 psi a psi b. This electron density is greater than in the case of atomic orbitals. If an electron enters bonding molecular orbital, the electron density between two nuclei increases by this amount. It produces an attractive force between the nuclei and decreases the energy of the molecule. On the other hand, if an electron enters anti-bonding MO, the electron density between two nuclei decreases. On squaring equation 2, both the sides, we have psi a square is equal to psi a square plus psi b square minus 2 psi a psi b. If an electron enters anti-bonding MO, the electron density between two nuclei decreases by this amount. And due to decrease in electron density between two nuclei, a repulsive force is produced between the nuclei and it increases the energy of the molecule. And this is why the energy of bonding MO is lower while the energy of anti-bonding MO is higher. Let us represent it diagrammatically. These are two 1s wave functions of two hydrogen atoms. These have similar sign and therefore after linear combination there is constructive interference. This sigma 1s bonding MO, if an electron enters in this sigma 1s bonding MO, the electron density between two nuclei increases and an attractive force acts between this electron density and the nucleus of hydrogen atom. And this is why the energy of the system becomes lower. On the other hand, in this case, two 1s atomic orbitals of two hydrogen atoms have different wave function sign. One has positive wave function sign while the other has negative wave function sign, and destructive interference will take place. As a result, when the electron enters this sigma 1s star, that is anti-bonding MO, the electron density between two nuclei decreases, and as a result a repulsive force acts between two nuclei and the energy of the system increases. This is anti-bonding MO. The Aufbau principle, Hund's rule, and Pauli's exclusion principle are applicable to molecular orbitals also. These principles, Aufbau principles, Hund's rule, and Pauli's exclusion principles are generally applied to atomic orbitals, but these can be applied to molecular orbitals also. If there are two orbitals and only one electron is to be filled up, the electron will fill up in the molecular orbital of lower energy according to Aufbau principle. If two molecular orbitals are available having the same energy, electrons will fill up one by one, and when both the orbitals are singly occupied, pairing of electron will start, and it is in accordance with Hund's rule. According to Pauli's exclusion principle, maximum 2 electrons in any orbital can be accommodated. Maximum 2 electrons can be accommodated in any orbital, whether it is atomic orbital or molecular orbital. Each electron pair of the bonding MO constitutes one covalent bond, while each electron pair of the anti-bonding MO cancels one covalent bond, and therefore the number of bonds, that is the bond order in a molecule, is given by the following relationship. Bond order is equal to Nb minus Na by 2, where Nb is number of electrons in bonding MOs and Na is number of electrons in anti-bonding MOs. And this number is divided by 2 because 2 electrons constitute one covalent bond. MOT applied to octahedral complexes. During the formation of an octahedral complex, 6 ligands approach the central metal line along the axis. There are 2 ligands on the x-axis, 2 ligands on the y-axis, and 2 ligands on the z-axis. During the formation of an octahedral complex, 6 ligands approach the central metal ion along the axis. There are 9 atomic orbitals present in the valence shell of first row transition metal ion, that is 3D transition metal ion, and these have been represented diagrammatically below along with their symmetries. This is 4s atomic orbital which has symmetry A1G. Its lobes are present on the axis, x-axis, y-axis, and z-axis. This is 4px whose lobes lie on x-axis, 4py whose lobes lie on y-axis, and 4pz whose lobes lie on z-axis. These orbitals have symmetry T1u. 3dxy, 3dyz, and 3dxz orbitals have symmetry T2g. The lobes of these d atomic orbitals lie in between the axes, while 3dz square and 3dx square minus y square orbitals have lobes along the axis. The symmetry of these orbitals is easy. It is obvious from the above figures that out of these 9 atomic orbitals, the lobes of 6 atomic orbitals, 4s, that is A1G symmetry, 4px, 4py, and 4pz, that is T1U symmetry orbitals, and Eg, 3dz square and 3dx square minus y square. The lobes of these 6 atomic orbitals, 4s, 4px, 4py, 4pz, 3dz square and 3dx square minus y square, the lobes of these 6 atomic orbitals lie on the axis, that is along the metal ligand direction, and hence they are suitable for sigma bonding with ligands in octahedral complex, because a sigma bond is formed by linear overlapping of atomic orbitals. Each monodentate ligand L contains one sigma type orbital containing a lone pair of electrons. Each monodentate ligand L contains one sigma type orbital containing a lone pair of electrons. These 6 sigma orbitals of 6 ligands take part in linear combination forming 6 ligand group orbitals, LGOS, of symmetries A1Z, T1U, and Eg. Please note that these are the symmetries of atomic orbitals of central metal line whose lobes lie on the axis, which are suitable for sigma bonding with ligands, and accordingly 6 sigma orbitals of ligands take part in linear combination forming 6 ligand group orbitals with matching symmetries, that is A1G, T1U, and Eg. The metal sigma orbitals overlap with ligand group orbitals with matching symmetries forming molecular orbitals for the octahedral complex. The 6 atomic orbitals of the metal, that is sigma orbitals of the metal, overlap with ligand group orbitals with matching symmetries forming molecular orbitals for the octahedral complex. And it is the molecular orbital energy level diagram for an octahedral complex having only sigma bonding. These are d atomic orbitals, 3d, 4s, 4p. D atomic orbitals of the central metal line have symmetry Eg and T2g, while 4s has symmetry A1g and 4p has symmetry T1u. Out of these 9 MOs, 1, 2, 3, 4, 5, 6, 7, 8, 9, the atomic orbitals which are suitable for sigma bonding are T1u, A1g, and Eg. The 6 sigma orbitals of ligand take part in linear combination forming 6 ligand group orbitals with symmetries A1G, T1U, and Eg. The A1G ligand group orbital overlaps with A1G orbital of metal forming A1G bonding MO and A1G star anti-bonding MO. Similarly, T1U ligand group orbital overlaps with T1U orbital of CMI forming T1U bonding MO and T1U star anti-bonding MO. And similarly, the Eg ligand group orbital overlaps with Eg atomic orbital of central metal ion forming easy bonding MO and Eg star anti-bonding MO. The electrons, each ligand contains one pair of electrons and hence 6 ligands will contain 6 pair of electrons. These 6 pair of electrons are filled up in these 6 bonding molecular orbitals 1, 2, 3, 4, 5 and 6. 6 electron pairs of ligands occupied 6 bonding MOs. Please note that the T2G orbitals of the CMI have lobes in between the axes and hence they are not suitable for sigma bonding in an octahedral complex and hence these remain non-bonding. The electrons of the central metal ion fill up in T2G non-bonding and Eg star anti-bonding MOs. This is the central part of the MO diagram of octahedral complex with sigma bonding only. The electrons of CMI occupy T2G non-bonding and Eg star MOs. Noteworthy facts regarding the molecular orbital energy level diagram for an octahedron complex with sigma bonding only. The T2G orbitals of the metal have their lobes between the axes and hence they are not suitable for sigma bonding and hence they remain non-bonding. The 6 electron pairs from the ligands are placed in lowest energy molecular orbitals, lowest energy bonding molecular orbitals A1G, T1U and Eg. The electrons of the metal ion are accommodated in non-bonding T2G and anti-bonding Eg star molecular orbitals. As we have discussed in the previous slide. The central part of the diagram is similar to d atomic orbitals are splitting as in the case of CFT. The central part of the MO diagram was similar to the splitting of d atomic orbitals in the case of crystal field theory, and the energy difference between Eg star and T2G MOs may be treated as crystal field splitting energy. It indicates the ionic character in metal ligand bond. The only difference is that Eg star MOs have some ligand character also, and it indicates the covalent character in the metal ligand bond. Thus, the molecular orbital theory incorporates the possibilities of both ionic and covalent character in the metal ligand bond. The energy of Eg star MO increases with the increase in the strength of ligand field. These are some noteworthy facts regarding the molecular orbital energy level diagram for octahedral complexes with sigma bonding only. Let us see the MO diagram of CONH3 whole 6 triple plus, which contains 6 NH3 ligands whose ligand group orbitals are present here. 6 ligand group orbitals 1, 2, 3, 4, 5 and 6 with symmetries A1G, T1U and Eg. And these are the atomic orbitals of cobalt triple plus ion. 3D, 4s, 4p, 3D have symmetry Eg and T2G, 4s has symmetry A1G and 4p has symmetry T1U. These 6 electron pairs of 6 NH3 ligands occupy the bonding MOs. 1, 2, 3, 4, 5, and 6. NH3 is a strong ligand, and therefore the energy of Eg star MO is above 4s atomic orbital, and the energy difference between this Eg star and T2G MOs may be regarded as delta O. This delta O is greater than pairing energy. The amount of energy required to pair off two electrons in a single orbital is called pairing energy. There are 6 electrons present in 3D orbitals of cobalt triple plus ion. The first electron will occupy here, first electron, second, third. If the fourth electron is promoted to Eg star MO, delta O amount of energy will be required, which is greater than the energy required to pair up the electrons in the single orbital, and therefore the fourth electron will occupy here. This is fifth electron and this is sixth electron, and thus CONH3 whole 6 triple plus ion has no unpaired electron. It is diamagnetic. Its magnetic moment is lower than free cobalt triple plus ion, and hence CONH3 whole 6 triple plus is a low spin complex having fewer number of unpaired electrons than in free metal ion. Let us see another MO diagram of COF6 triple minus. In this case, F minus is a weaker ligand and it produces a smaller electrostatic field around the CMI. Here the energy of Eg star MO is lower than 4s orbital, and in this case the energy difference between these two orbitals, which may be regarded as delta O, that is crystal field splitting energy in octahedral complex, is lower than pairing energy of electrons, and therefore this is first electron, second electron, third electron, and if the fourth electron is paired here up, the amount of energy required will be greater than the energy required to promote the electron to Eg star MO. Therefore, first electron, second electron, third electron, fourth electron will go here in the Eg star MO. This is fifth electron and it is sixth one. In these 5 molecular orbitals, electrons fill up one by one, and when all the 5 molecular orbitals are singly occupied, the pairing up of electron starts from the lower energy orbital. COF6 triple minus has the same number of 4 unpaired electrons as in the case of free transition metal ion, free CO triple plus ion, and therefore COF6 triple minus is a high spin complex having the same number of unpaired electrons as in the case of corresponding free transition metal ion. Thank you for watching the video with patience and concentration. If you have not subscribed my channel, please subscribe it so that you may get information regarding my new videos in time. Please like and share it also. Thank you again.